Welcome to the deep dive. Today, well, it's Earth Day, and we're doing something a bit different. We're zooming out, like way out, beyond our planet, to explore the story of the universe itself. And our guide for this cosmic journey, the James Webb Space Telescope, JWST.
That's right. And think of it less like, just a look of discoveries and more like a story unfolding, how everything came to be, from the Big Bang, basically, to galaxies forming, stars living and dying, and maybe even the ingredients for life popping up all over the place. JWST is giving us an amazing view of all that.
Okay, so JWST, we hear the name a lot, but what makes it so special for telling this story, especially compared to, say, Hubble?
Well, the key thing really is infrared. JWST is built for infrared light. Hubble, mostly worked in visible light, ultraviolet, some near infrared, but infrared, that's the game
So
changer.
why infrared, though? What's the advantage?
Okay, two big reasons. First, dust. Lots of cosmic action, like stars being born, happens behind thick clouds of dust and gas. Visible light gets blocked or scattered. But infrared light, it can cut right through a lot of that dust. So we see things Hubble just couldn't.
Ah, like X-ray vision for cosmic dust cloud?
Kinda, yeah. And the second thing, maybe even more important for the early universe story, is redshift. The universe is expanding, right? So the light from really distant objects, the oldest objects, gets stretched out as it travels towards us. Its wavelength shifts towards the red end of the spectrum and often right into the infrared. So to see the universe's baby pictures, you need a powerful infrared telescope.
Got it. So it's not just about seeing through dust, it's about seeing that stretched out light from the beginning of time.
Exactly. And while Hubble was amazing, JWST is maybe more accurately seen as a successor to the Spitzer Space Telescope, which was also infrared. But JWST is just vastly more sensitive, much sharper.
Okay, so we've updated from maybe a grainy photo to like high-definition IMAX for the early cosmos.
Yeah.
Our mission today then is to follow that story. But first, let's give credit where it's due. Hubble, launched in 1990, named after Edwin Hubble. It changed everything, didn't it?
Oh, absolutely. Hubble was a revolution. I mean, over 1.6 million observations, more than 21,000 scientific papers. It's foundational. Think about what it showed us. Stuff flying between stars, comets hitting Jupiter, bang.
Yeah.
Pluto's moons, discovering those. Seeing the dusty disks where planets are forming around other stars, looking at exoplanet atmospheres, and peering back over 13.4 billion light years. It set the stage.
It really did. A true workhorse. And now JWST, this big international project, NASA, ESA, the Canadian Space Agency is taking us even further back. It looks at our solar system too and exoplanets, but today we're really focused on those cosmic origins. So let's dive into that first chapter, the cosmic dawn. What exactly was happening then?
Okay, cosmic dawn. That's roughly the first few 100 million years after the Big Bang, a really crucial time. Before that, you had the Dark Ages. The universe was basically filled with neutral hydrogen gas, kind of like a fog, opaque to a lot of light.
Yeah.
Then, the very first stars ignited. We call them population 3 stars.
Population 3, what were they like?
These weren't like our sun. They were monsters. Huge, incredibly hot, probably hundreds of times the mass of the sun, and they burned through their fuel super fast. And crucially, they were made of almost pure hydrogen and helium, the stuff created in the Big Bang itself. Very pristine.
Okay, so these giant, pristine stars appear, and they change things. They end the Dark Ages.
Exactly. They blasted out intense ultraviolet light, and this light started stripping electrons off those neutral hydrogen atoms. That's called ionization. Imagine the little bubbles of ionized gas forming around these first stars. Then those bubbles grew and merged. Eventually, over millions of years, the entire universe became reionized. The fog lifted, basically. It became transparent to UV light. Light could travel freely across space.
A cosmic sunrise. And that's the era JWST is built to see.
Precisely. It's like a cosmic time machine, peering back into that critical transition period.
We have that snapshot from earlier, the cosmic microwave background, right? From like 378,000 years after the Big Bang.
Yeah, the CMB is like the universe's baby picture. But there's this huge gap, hundreds of millions of years, between the CMB and when galaxies really got going. JWST is filling in that gap.
How does it actually do that? Is it just because the mirror's so big?
The big mirror definitely helps 6.5 meters across, collects way more light than Hubble's 2.4 meters, so it sees fainter, more distant things. But the real magic is how it measures that redshift we talked about, with an incredible precision.
Right. The stretching of light tells you distance, which tells you time. How does it measure the stretch?
It uses spectroscopy, mainly with an instrument called NIR spec, the near-infrared spectrograph. Think of it like passing the galaxy's light through a prism. It splits the light into its different wavelengths, its spectrum. and you see these specific patterns, fingerprints of different elements. By seeing how much those fingerprints are shifted towards the red, we know exactly how much the light stretched, and thus how far back in time we're looking.
Okay, so spectroscopy gives you the precise distance.
Yeah, the spectroscopic redshift. It also uses photometry with NIRCam, the near-infrared camera. That involves measuring the brightness through different filters. Analyzing that pattern of brightness, the spectral energy distribution, or SED, also gives clues about redshift and the galaxy's properties. But spectroscopy is usually the gold standard for confirmation.
And these techniques are already finding things. Like that JADES galaxy, JWST 14-0, that sounds really far back.
Oh, it's staggering. The light from that galaxy started its journey when the universe was only about 285 to 290 million years old. That's a redshift of around 14.
Wow. 2% of the universe's current age.
Something like that, yeah. Tiny. And crucially, that redshift 14 isn't just an estimate from the brightness and colors it's confirmed with spectroscopy. We know it's genuinely that far away and that old. The JDS program, which stands for JWST Advanced Deep Extragalactic Survey, is finding others in that ballpark too, pushing the frontiers.
It's just wild to think of galaxies forming that quickly. And this is shaking things up, isn't it? Our models didn't expect this.
They really didn't. That's one of the biggest surprises so far. Some of these very early galaxies look surprisingly mature. They're more massive, brighter, and seem to have more heavier elements, what astronomers call metals, than our models predicted should be possible so early on.
So heavier elements than just hydrogen and helium, stuff made in stars.
Exactly. Elements like oxygen. Finding significant amounts just 300 million years after the Big Bang, well, that implies stars formed, lived, died, and enriched their surroundings much faster than we thought.
These are the early bloomers then, galaxies that grew up too fast.
That's a good way to put it, yeah. The standard picture was more gradual. Stars start forming maybe 300, 400 million years after the Big Bang. Then smaller bits merge together slowly over hundreds of millions, even billions of years, to build up big galaxies. But JWST is seeing surprisingly hefty developed galaxies already in place back then. It's forcing a rethink. Maybe galaxies could form much more rapidly, perhaps from the direct collapse of huge gas clouds, not just this slow merging process.
And it's not just size and chemistry, right? I heard something about finding galactic bars really early too.
Yeah, that's another head scratcher. Galactic bars, those big, elongated structures of stars you see in the center of many spiral galaxies, including our own Milky Way. We thought those took a long time to form, billions of years, as the galaxy disk settles down and evolves. But JWST has found evidence for bars in galaxies just a few 100 million years old.
That's crazy. So things were organizing themselves much faster.
It suggests really rapid mass assembly and metal enrichment, as the researchers put it. Our computer simulations are struggling to replicate that speed. It's a real puzzle.
So the models need tweaking. But what about even earlier? You mentioned redshift 14 confirmed. Are we seeing lots at redshift 15, 16, 20?
That's an interesting point. After the initial excitement, finding confirmed galaxies at those really high redshifts, say above 15, seems maybe a bit harder than some anticipated. There are candidates based on photometry, some maybe even up to redshift 20, which is like 200 million years after the Big Bang. But getting that spectroscopic confirmation is tough. It could mean galaxy formation really did drop off sharply before about 300 million years. Or maybe they're just harder to find or identify than we thought. It's an active area figuring that out.
Okay, so JWST is rewriting Chapter 1 of cosmic history. But it's not just about galaxies, is it? It's finding clues about the ingredients for life.
Absolutely. This is where it gets really profound, I think. Remember JD's GSC 14-0, that redshift 14 galaxy?
Yeah, the record holder.
JWST detected oxygen in it. Clear spectral signature of oxygen. It's the most distant oxygen ever found, just 290 million years after the Big Bang.
Oxygen? Why is that so significant so early?
Because oxygen isn't made in the Big Bang. It's forged inside stars through nuclear fusion, then scattered when those stars die. Finding it so early tells us that first generation of stars, those population 3 stars, must have formed, burned through their fuel, and exploded relatively quickly to enrich the gas that formed this next galaxy. It means the building blocks for planets, for water, they were already starting to accumulate very, very early on.
Wow, the ingredients were there. And what about more complex stuff, organic molecules?
Yes, even more amazing perhaps. JWST made its first detection of complex organic molecules in an even earlier galaxy, light from over 12 billion years ago. We're talking things like methanol, maybe acetylene, ethane, basically complex molecules containing carbon. Think of it as cosmic soot or smoke.
How did they even see that so far away?
They got lucky with a natural telescope. The light from this distant galaxy passed by a massive galaxy cluster closer to us. The gravity of the cluster bent and magnified the light from the background galaxy, a process called gravitational lensing. It created this distorted, brightened image called an Einstein ring.
Nature's magnifying glass.
Exactly. And that magnification boost allowed JWST's instruments to pick out the faint signatures of these complex molecules.
Okay, finding complex organic molecules 12 billion years ago. What does that imply? That's huge, isn't it?
It's incredibly exciting. It means the raw materials needed for life as we know it weren't just present, but forming relatively early in cosmic history. It adds weight to ideas like panspermia, the notion that life's ingredients could spread through space, maybe on asteroids or dust. It suggests the universe might have been, chemically fertile for life much earlier and maybe more commonly than we used to think.
So the potential for atmospheres, oceans, the stuff life needs, maybe it was kind of baked in from the early stages.
And that's the tantalizing possibility, yeah, that the universe was primed for biology fairly early on. Makes you wonder.
Definitely makes you wonder. Okay, let's shift gears slightly. We can't talk about JWST without mentioning the images. They're just breathtaking. But they're more than just pretty pictures, right?
Oh, absolutely. They are stunning, aren't they? The pillars of creation, reimagined, the Carina Nebula cliffs, the Tarantula Nebula. But every pixel in those images is data. Rich scientific data.
Even things like the deep fields, SMACS 0723, or Pandora's cluster, which look almost abstract.
Packed with information. Pandora's cluster, for example, shows the gravitational lensing effect again, distorting background galaxies and letting us study them.
And the colors, they're not just chosen to look nice.
No. They're assigned based on the different infrared wavelengths JWST observes. Each filter captures light from a specific slice of the infrared spectrum. So by looking at how bright something is in different colors, different infrared filters, scientists can figure out its temperature, what it's made of, even how fast it's moving.
So the images tell stories about the physics and chemistry happening out there.
Exactly. They show us the entire life cycle of stars. We see them being born in these beautiful dusty nurseries like the Pillars or Orion. We see them evolve, and we see them die, like in the Cassiopeia, a supernova remnant image, where JWST shows the expanding shell of debris in incredible detail. And again, because it's infrared, it pierces through dust that would hide a lot of this from Hubble. You can see stars forming inside the dust cocoons.
It's that ability to see through the dust that seems so key.
It really is. There are amazing comparisons. Hubble's view of merging galaxies, then Spitzer's infrared view showing the hidden star formation, and now JWST takes that to a whole new level of clarity and detail.
It connects you emotionally, the beauty, but also scientifically. Amazing. Okay, let's pivot again. Exoplanets. Worlds beyond our solar system. How is JWST contributing there?
Big time. It's a major part of its mission. One key target has been the TRAPPIST-1 system. Remember that one? 7 rocky planets around a small, cool red dwarf star.
Yeah, lots of excitement about potential habitability there.
Right. Well, JWST has started studying their atmospheres, or lack thereof. Early results for one of them, TRAPPIST-1c, suggest it probably has a very thin atmosphere, maybe none at all. Possibly too hot, too close to the star, lost its air.
Ah, okay. So maybe less habitable than hoped, at least that one.
Seems that way for TRAPPIST-1c, yeah. It dampens the prospects a bit. There's still other planets in that system to study.
And it's looking at other rocky planets too, ones closer to Earth's size.
Definitely. It's following up on candidates found by missions like TESS. JWST has confirmed some of these are indeed rocky planets. And the next step, the really exciting part, is using spectroscopy to sniff their atmospheres, looking for the chemical fingerprints of molecules.
Like water, methane, stuff that might hint at life.
Biosignatures? Exactly. Water vapor, methane, carbon dioxide. Detecting those in the atmosphere of a rocky planet in the habitable zone. That would be a monumental discovery. We're not there yet, but JWST has the power to potentially do it.
That really is the holy grail, isn't it? What about other kinds of objects, not just rocky planets?
Oh yeah. Looking at brown dwarfs, those objects that are bigger than planets but didn't quite make it to becoming stars, failed stars. And JWST is getting amazing atmospheric data from them. It's found silicates basically, clouds made of tiny sand or rock particles, plus methane, water, CO2, carbon monoxide, sodium, potassium. A whole chemical soup. Helps us understand how these things form.
Clouds of sand. Wild. And hot Jupiters, those giant planets really close to their stars.
Yep. JWST is studying their atmospheres too. It's even been able to create temperature maps of some, like WSP-18b, showing how heat is distributed across the planet's surface. Gives us clues about their winds and weather.
It's just incredible detail. Is it also seeing planets actually forming?
It is. It's observing the disks of gas and dust around young stars where planets are born, protoplanetary disks. It looked at the disk around a young red dwarf called AU Microscopiae, for instance. Seeing how these disks are structured and what they're made of helps us understand how planets like ours, or completely different types, come into being.
So it's seeing the whole picture, from the birth disks to mature planets and their atmospheres. Amazing diversity out there.
Truly is.
Okay, another huge topic, black holes, especially the supermassive ones at the centers of galaxies. What's JWST telling us about them?
Well, another surprise. When JWST looks back at the very early universe, it's finding supermassive black holes that seem, well, too big, too soon. According to our standard models of how black holes grow, basically by swallowing gas and merging with other black holes, some of these early ones seem to have grown much faster than we thought possible.
Faster than the speed limit. There's a theoretical limit, right? The Eddington limit.
Exactly. The Eddington limit describes how quickly a black hole can theoretically pull in matter due to its gravity before the radiation pressure from that infalling, heating up matter, pushes back and chokes off the inflow. Some of these early black holes seem to have grown at rates at, or maybe even exceeding that limit. How they did that is a big question. Did they start from bigger seeds? Did they have ways to accrete matter more efficiently? We don't know yet.
Another fundamental process that needs rethinking, thanks to JWST. And what about the relationship between these black holes and the galaxies they live in?
JWST is crucial there too, especially by looking at galaxies that are merging. We think galaxy mergers play a big role in feeding gas to the central black holes, making them grow, and also triggering bursts of star formation in the galaxy itself. But these mergers are often incredibly dusty events. Hubble couldn't see into the messy cores very well. JWST's infrared eyes cut through that dust, letting us see the black holes interacting, the gas flows, the triggered star birth, to give us a much clearer picture of that coevolution of black holes and galaxies.
Seeing through the dust again seems to be a recurring theme.
It's a huge part of its power, yeah.
Okay, we've covered early galaxies, life ingredients, exoplanets, black holes. Any other standout discoveries from JWST so far? There must be loads.
Oh, absolutely. I mean, even closer to home, it detected and helped characterize a really small asteroid, just the size of a building, 2024 YR4. Good for planetary defense knowledge. It's also getting amazing compositional data from objects way out past Neptune, the TNOs, detecting different ices, complex hydrocarbons. Tells us about the raw materials of the outer solar system.
Stuff left over from the beginning.
Pretty much. And speaking of solar system structure, it found something weird in the Fomalhaut star system. Not just an asteroid belt and a Kuiper belt like ours, but like 3 belts, including an unexpected intermediate one.
So planetary systems might be even more varied than we thought.
Seems like it. It's also given us stunning new views of Uranus, seeing its rings and polar caps in infrared like never before. And maybe one more really weird one. Finding these Jupiter-mass objects just floating freely in the Orion Nebula, not orbiting stars. Rogue planets. Some are even in pairs. How do they form? Were they kicked out of systems? Did they collapse on their own like stars? More mysteries.
It's just, the sheer range is incredible. Now, operating such a complex machine in space, it hasn't all been perfectly smooth sailing, has it? Were there glitches?
Well, the initial deployment in mirror alignment was unbelievably complex, and it went incredibly well. Better than expected, actually. But yeah, like any cutting-edge technology, there have been a couple of minor bumps. The mid-infrared instrument in IRI had an issue with one of its observing modes for a while, and the near-infrared imager, 9 rays, had a communications delay problem early on.
Okay, but they fixed them.
Yep. The teams on the ground worked through them, found solutions or workarounds. All the instruments are currently working really well, exceeding their original performance goals in many cases. It's been remarkably successful operationally.
That's great to hear. And how long is it expected to last? And how does the science actually happen? Who gets to use it?
It was designed for a minimum mission of 10 years. But the launch was so precise, and it's been so efficient with its fuel for station keeping out at L2, that estimates now suggest it could potentially operate for 20 years, maybe even longer, which is fantastic news for astronomy.
Wow, 20 years. That's amazing.
As for the data, scientists propose observations, and time is awarded competitively based on scientific merit. Those teams get exclusive access to their data for 1 year. After that year, all the data goes into a public archive, available for anyone in the world to download and analyze. So we're constantly getting new science from older data, too, as more people look at it.
So there's a flood of data coming out now from Cycle 1, and Cycle 2 is underway.
Exactly. And let's not forget Hubble. It's still up there doing great science, even with fewer working gyroscopes. They work together really well, Hubble and Webb, complementing each other's capabilities.
That's a great point. So wrapping up this deep dive, what's the big picture takeaway for you from JWST so far?
For me, it's just how fundamentally it's changing our view at every scale. From the literal dawn of time to planets around nearby stars, it's confirming some things we expected, but in stunning detail. But maybe more importantly, it's throwing up these huge surprises. Things like how fast those first galaxies formed, how big the first black holes got. It's forcing us to go back to the drawing board on some really fundamental ideas about how the universe evolved. It's challenging us.
Yeah, it really feels like we're peeling back layers and finding the universe is even more intricate and maybe even stranger than we thought. And it makes you want to just stare at those images and try to absorb it all.
Definitely. I hope people do. Go look at the images online. They're not just pretty. They're windows into these incredible processes. And maybe the thought to leave everyone with is, what's next? What other huge secrets are hiding out there that JWST might uncover in the next, 5, 10, 15 years? How will it change our understanding of our place in it all? And, that ultimate question about life elsewhere, that will JWST give us the first definitive clues? It's just an incredibly exciting time.
It really is. Profound questions to ponder. We definitely encourage you, our listeners, to check out those JWST images and read more about these discoveries. Let us know your thoughts. What blew your mind the most? We'd love to hear from you. Thank you so much for joining us on this cosmic journey with the James Webb Space Telescope here on The Deep Dive. If you enjoyed this, please subscribe to our channel for more deep dives into science and discovery. And maybe share this with a friend who looks up at the stars and wonders. Until next time, keep looking up.